This is Math 154, and we're beginning Unit 3. In your textbook, it's section 7.1. As we begin this unit, I just want to kind of mention that up until now, we've been emphasizing the applications of integrals. So we've actually been doing a lot of the integration itself using our calculators. In this chapter, this unit, we're going to return to studying the actual process of integration. And we're going to start looking at some more challenging integrals to do. You learned back in Calc 1 that no matter how good we get at integration, there are certain integrals that we can never do by hand. The antiderivatives simply don't exist. However, there are some creative tricks and techniques that we can learn that will help us do more antiderivatives than what we know right now. So section 7.1 is primarily a review. It's essentially a review of basic integration techniques with the emphasis on some of the little tricks and tips. These are all things that we have seen before, but I'm kind of trying to gather them all in one place. So, a few things to keep in your mind. First of all, use substitutions. This technique happens so often, I'm not going to say much about it because we'll be using it as a subset of many of our other techniques, and it's one you've used a lot. All right. Tip number 2. Look for things that you can factor or expand. Sometimes that helps. In our 2 examples, we're going to see how this works. In example 1, the typical choice of u would be the inside function, what's under the radical. So if I let u be what's underneath that square root, then du would be 3x squared plus 2x, and the dx I'm just going to bring over here right away. Now, at a very quick casual glance, we might think, hey, we don't have that over here. But of course, it doesn't take much to realize that when we expand and distribute that numerator, that's exactly what we have. So I could simply rewrite this as 1 over the square root of, that's the u, and then all of this, 3x squared plus 2x dx, is really all the du. That makes this fairly easy to take the antiderivative. That's really u to the negative 1/2. So the antiderivative would be u to the positive 1/2. Dividing by 1/2 is actually the same as multiplying by 2. I'll put that in the next step. Plus c. So I'd have 2 times. That's the square root. And I'm going to put the u back in. And there's my antiderivative. Okay. So expanding, multiplying something out. Just something to consider as you're looking at these problems. The opposite of expanding would be factoring. That's another option. When I look at example 2, right now, I don't see anything that's a true inner function. We have talked about letting u be what's in the denominator. But I'm going to notice here, I don't think that's going to help me too much, because the derivative would be 2e to the 2x plus 2e to the x, and I don't have any e to the 2x's on top. So instead, I'm looking at that denominator thinking, actually, that looks like I could factor it. I think that's a perfect square. Isn't that just e to the x plus 1 times itself, or squared? Right? E to the x times e to the x would be e to the 2x. Outers and inners will be 1 e to the x. When you add them, you'll get 2 e to the x plus the 1. So by factoring, I've created a true inner function and a really good option to let u be e to the x plus 1, what's inside that square. The derivative would still be e to the x, and I'm going to bring the dx over. So here is my du. Gotta find du. If I don't, I'm in trouble, right? But we found it both times, so we're good. That's actually 1 over u squared. And then all of this is du. I'm thinking of that as a u to the negative 2. So when I integrate, I'll get u to the negative 1 divided by negative 1 plus c, or minus u to the negative 1 would be 1 over u, and I'll put the u back in. Oops. So just keep an eye out for expanding and factoring, both useful techniques that serve us well sometimes. All right, our next little trick is separation. This sometimes helps in integrals that involve fractional expressions. They're sometimes made easier if we integrate by splitting up the numerator. I want to really emphasize that. It's only the numerator that can be split up, not the denominator, right? If we look at the example, you'll see exactly how that works. As I look at this, I could split that up as 4 over e to the 3x for one integral, and then e to the negative 2x over e to the 3x as a second separate integral. Because there's a common denominator, I would be able to add those back together and get back what I started with, right? Notice, and I'm just going to show this as sort of a sidebar here, that does not work for denominators. If I had something like 5 over 2 plus x, that's not the same as 5 over 2 plus 5 over x, right? To truly add those fractions, you'd have to get a common denominator and put them together, and you would not get that. So never split up denominators. It's okay to split up numerators by keeping that common denominator with both of them. All right, why would I want to do that? Well, of course, I'm trying to make this easier to integrate, and I think I have. I could rewrite this first one as 4 e to the negative 3x dx. That's actually a pretty simple little u substitution, right? If we just let u be the negative 3x, so I'm not too worried about that one. And here, I could simplify that by subtracting the exponents. Negative 2x minus 3x would give me e to the negative 5x. So in both cases, I've just got pretty straightforward u substitutions to go from here. This first one, u would be negative 3x. So du would be negative 3 dx. And I'd have negative 1/3 du equal to dx. So I'm going to have the integral of, let's see, I'm going to pull that 4 out, well, yeah, I'll pull the 4 out in front. And then I've got e to the u. And then I'm going to replace the dx with negative 1/3 du. Negative 1/3 I'll pull out in front, put the du in here. Let's finish that one up. That's going to give us negative 4/3. Sorry, I'm running out of space here. Integral of e to the u is still e to the u, so that would be e to the negative 3x. I'm going to hold off and put my plus c at the very end when I do the second one. So plus, this guy's same idea. U is negative 5x, so du is negative 5 dx, and we end up with a negative 1/5 du equal to dx. So I've got e to the u, replace the dx with negative 1/5 du. And actually, I'm going to end up with a minus. Let me fix that. 1/5 e to the u, or e to the negative 5x, plus c. And there, just barely made it as my final answer. Okay, so splitting up the numerator, only the numerator, of a fraction, common algebra trick. I think I've got one more like that. There we go. I didn't mention this last time, but we should always verify that we can't just leave it the way it is. And of course here the obvious u would be 4 minus x squared. The derivative would be negative 2x dx. The x would be fine, but I wouldn't have anything to do with that 1. So I'm going to say, since I can't do a basic u substitution, let's try splitting up the numerator. I'll have 3x over that denominator as my first integral, and then just 1 over that denominator as my second. Again, notice I'm keeping the common denominator. I could put them back together and I'd get right back what I started with. I never want to change the problem. I can change the appearance, but I can't change the value. All right, this now appeals to me as a u substitution because the derivative is negative 2x and I've got the x right there. We can always fix constants, right? So let's do the first integral with a u substitution. We'll let u be what's under our radical. So du would be negative 2x dx, and negative 1/2 du equals x dx. So that x dx I'll be replacing with a negative 1/2 du. So I have, let's see, I'm going to pull the 3 out in front, and then I've got the integral of 1 over the square root of u. And then here's that x dx, which I'm replacing with a negative 1/2. I'll put that in front. And a du. Let's just go ahead and finish that one, then we'll come back and work on this one. So I have negative 3/2. Integral of u to the negative 1/2 is u to the positive 1/2. Dividing by a half is the same as multiplying by 2 over 1. And again, I know there's a plus c, but I'm going to wait till I finish the whole thing before I put it in. 2's will cancel here, so I get a negative 3 square root of my u, which is 4 minus x squared. All right, let's come down to this next one. I know a u substitution won't work because I don't have the x dx that I would need to make that work. But that looks a little bit familiar to me. I think we've studied that one before, back in Calc 1. If you go to your list of integrals from your formulas list, handy little list, right? There's a whole big page of integral rules. This one looks a whole lot like that very first one, on the second column, actually. Okay. Looks really good. The a here, notice, would be 2. 4 is the a squared. X squared matches perfectly, so I'm just going to get an inverse sign, or I kind of like to write them as arc sign, of x over, in our case, 2. And bring that down. Add on my constant of integration, and I'm done. So splitting up a numerator of a fraction, pretty common trick, often works out very well. All right, here's the next trick, one that we've talked about before, and I know it's a favorite, being a little sarcastic there, trig identities. When we have relatively complex trig functions, it does not hurt a bit to keep your list of trig identities kind of front and center for you. We may need them at any time, so again, keep in mind that list of formulas, real handy. When I look at this first example, my problem here is my usual choice is to let u be what's inside something, but the sine is being cubed and the cosine is being taken to the fifth power. And so which one would I use? Well, the answer is neither one is actually going to help me out all that much. In this particular case, and I'll let you kind of prove it to yourself if you want to, letting u be sine x doesn't go anywhere, and neither does letting u be cosine x. Instead, I'm going to see if I can do some rewriting. I'm going to say, I know sine over cosine is tangent. So what if I took 3 factors of the cosine to go with these 3 factors of sine? With the idea that that would make a tangent cubed x. And then I'd have times the other 2 factors of the cosine over here. Again, always check to make sure you haven't really changed anything. If I were to multiply this out, the numerator would still be sine cubed x. The denominator would still be cosine to the fifth of x. So we haven't really changed it. It just looks a little different. All right, that's now tangent cubed x. And 1 over cosine is secant, so that's secant squared x. This may not look like we've accomplished anything because we still have 2 separate trig functions, both raised to powers. But I kind of remember that the derivative of tangent is secant squared, so that makes me feel like I'm on the right path to a good u substitution. If I now let u be the tangent of x, right, so this is actually u cubed, then the derivative would be secant squared x. And I'll bring the dx over, which is great because I have that sitting right here. So I'll think of this as u to the third, and then all of that just becomes du. Integrating will give me 1/4 u to the fourth, plus my c, or 1/4, that would be tangent to the fourth of x, plus c. All right, let's try another trig identity problem. Integral of sine x, sine 2x, dx. Mixing and having different arguments of the trig functions is almost always a problem. So when I see this, I try to get rid of that difference in arguments. And in this case, I'm thinking the double angle identity for sine is probably a good choice, right? Remember, there are double angle identities. Sine 2 theta is 2 sine theta cos theta, or in our case, we'd have 2 sine x cos x. So let's use that identity first of all. Which I could pull the 2 out of the integral just to kind of get it out of my way. And then I'd have sine squared x, cosine x, dx. All right, at least all the arguments are the same. Now, if I were looking for a u substitution, an inner function, the sine is inside the squaring function. And furthermore, the derivative of sine is cosine, which is perfect, right? So let's let u be the sine of x. Derivative of sine x is simply cosine x, and I'll bring the dx over. And there that is. I've got the du that I need perfectly. So I've got my 2 out here. That will become u squared. And then all of this just becomes du. So I have 2 times 1/3 u cubed plus c, or 2/3, and u is sine x, so that would be sine cubed x, plus c. So a couple of examples. Don't discount those trig identities. They can be really helpful. All right, a couple more tricks for us here today. The next one is sometimes when you have a fraction, multiplying by a form of 1 can be very helpful. Now, what exact form of 1 you want to use, that's where your creativity has to come into play. I know it sounds weird to say creative when it comes to math, but this is a chance. This technique is particularly common when you can multiply by a conjugate, and we'll see that. But it's also frequently used to get rid of negative exponents. And I'm actually going to do that example first. Here I've got the integral of dx over x to the negative 1 plus x to the negative 3. Now, unfortunately, those aren't multiplied. If they were, I could just move them up and make them positive exponents, right? But I can't do that when there's addition and subtraction. They're separate terms. Can't split them up since they're in the denominator. I'm stuck with them. So what I'm going to do is I'm going to say, let's multiply by a form of 1. I'm going to specifically choose x cubed over x cubed. The reason, of course, being that's going to kind of get rid of all the negative exponents, right? I picked the opposite of the most negative exponent. And what that's going to do is it's going to give me an x cubed on top. And on the bottom, I'll have x squared plus x to the 0, which is just 1. And that dx I'm just going to put out here. Now, unfortunately, I've got something here, and I haven't given you this trick yet. We're going to be talking about this trick more specifically in a couple of minutes. But another one of the tricks we're going to talk about is the fact that anytime you've got an algebraic fraction where the degree of the top is bigger than the degree of the bottom, the best thing you can do is usually long division. So I'm actually just going to divide this out. See if I can squeeze that in over here. If I take x squared plus 1 and divide it into x cubed, x cubed divided by x squared is x. That's going to make that x cubed plus x to the first. I need to subtract. Those will cancel out, and I'll get a remainder of minus x. So what I'm going to do is rewrite this whole integral as the quotient x plus the integral of the remainder minus x over x squared plus 1 dx. That's really typical, again, when the numerator's degree is bigger than the denominator's. Do your long division. Quotient goes in one integral, and then separate that from the remainder in the second integral. Quotient's usually easy to integrate, just like it is here, 1/2 x squared. And then here, I'm thinking we can use a u substitution. If u is the denominator this time, the derivative is 2x, and I've got the x right there. So let's do a quick little u substitution here. I'm going to let u be that denominator, x squared plus 1. du is 2x dx. So 1/2 du is x dx. So I'm going to do a couple things here. I'm going to pull that negative out. Probably should have just made that a minus, but I'll do that in the next step. And then my x dx is going to become the 1/2 du in just a moment. That x squared plus 1 is in the denominator, so I'm going to make that a 1 over u. And then here we go, replace the x dx with a 1/2 du. So I have 1/2 x squared first of all, then I'm going to have a minus 1/2, And the integral of 1 over u, that's the natural log of u, right? So natural log of my u, which is actually x squared plus 1. I didn't bother with the absolute values since it's already positive anyway. And then my constant of integration. And there we go. All right, so again, when you've got more than one term, addition or subtraction with some negative exponents, there's a good way to get rid of them. Multiplying by a form of 1, in this case, it was x cubed over x cubed. Example 2. Here's an example where we really do have a good conjugate. I know I can't do this directly because if I let u be that denominator, the derivative is minus sine x, and I don't have a sine x in here anywhere. So u substitution won't work, or at least not yet. Instead, I'll multiply by a form of 1, specifically the conjugate of the denominator, 1 minus cosine x. Let's just see what happens. Numerator, 1 minus cosine x. Denominator becomes 1, and of course the outers and inners cancel like they always do with conjugates. And then I'll get a minus cosine squared x. I'm tempted by a u substitution right now, but I got to be careful. If I let the denominator be u, the derivative is not just negative 2 cosine x, right? There'd be a chain rule times a sine x. And again, I don't have a sine x in there anywhere. So I don't think a u substitution will work yet. Instead, I'm looking at that thinking, that looks like a maybe trig identity situation. 1 minus cos squared x. That's just a version of this, isn't it? If I move that sine squared to the other side, cos squared is 1 minus, or excuse me, I have 1 minus cos squared. If I move the cos squared to the other side, 1 minus cos squared is sine squared. So I'm going to use the trig identity just to replace that denominator with sine squared x. All right, I'm using all my former ideas here. Not only do we multiply by a conjugate, but now we've used a trig identity. I'm still not seeing a good substitution, so I'm going to use another trick. Let's separate. I now have a single denominator with subtraction in the numerator, so I should be able to separate that as the integral of 1 over sine squared x dx. And then I'll make minus the integral of cosine x over sine squared x dx. All right, starting to see the light at the end of the tunnel. Bit more trig identity work. That's just cosecant squared. And that's an integral we know, right? Just as a reminder. Oops, I need integrals here. Cosecant squared is something we know how to integrate. So we're good here. And then what about this one? Cosine over sine squared. Well, I have to make it look like one of these, or I'm not going to be able to do it. I know cosine over sine is cotangent, and then the other 1 over sine is cosecant, so I'm kind of thinking maybe I can get here. Right? If I just sort of mentally think, okay, this is cosine x over sine x, and that's 1 over sine x. I can rewrite that as cotangent x, cosecant x. And that's something I can deal with. So let's do that. Your whole goal on these, cosecant x, is always to get these to look like something that you know the antiderivative for. I'm now just about done. I just take everything right off the tables. The antiderivative of cosecant squared x is negative cotangent x. Subtract. The antiderivative of cotangent cosecant was a negative cosecant x. Got our plus c. So I end up with, I'm just going to write the positive one first, cosecant x minus cotangent x plus c. All right, one more example of multiplying by a form of 1, specifically a conjugate. Here we are with the common situation for conjugates, right? Our denominator, 4 minus the square root of x. That's one that we see conjugates with a lot. So let's go ahead and do that. Let's multiply by 4 plus the square root of x, top and bottom. And let's see, this one's a little bit lengthy, so I'm going to warn you ahead of time. You might want to have a spare sheet of paper or write small, one or the other. I won't write too small so you can't see it, but I may end up needing extra paper. We'll see. All right. Numerator, 4 plus the square root of x. Denominator, multiplying this out would give me 16. Again, outers and inners will cancel. And for the lasts, minus the square root of x squared, or just minus x. All right, so let's see here. We have an integral where we've got a denominator and we've got a numerator with 2 pieces. Splitting this up into 2 separate fractions has been working pretty well for us, so let's do that. I'd have the integral of 4 over 16 minus x dx plus the integral of square root x over 16 minus x dx. This one I believe I can do with a pretty simple u substitution. If I just let u be the denominator now, the derivative will be negative 1. No problem, right? So let's do that. U is 16 minus x. Du would be negative 1 dx. And actually I can just move that negative to the other side like so. Dx is minus du. So I end up with the integral of 4 over u. And I'll replace the x with a minus du. And I'm just going to finish this one. That gives me negative, and I'm going to pull the 4 out. And that'll become a 1 over u, so the antiderivative would be the natural log of u, which is 16 minus x. Again, I'm going to hold off till the very end to put the rest of it there, and then I'll do the plus c. All right, I'm going to make some space over here. We'll fill that in when we're completely done. But I'm going to have to do some work to deal with this one. I have got the integral of square root x over 16 minus x dx. I'm going to use another trick of multiplying by a form of 1 again. And this is not one that you might necessarily think of if you hadn't seen it before, so it's one I'm just going to show you, something to kind of keep in mind. Right now, I can't just let u be the denominator. We saw the derivative was just negative 1, and I'd have an issue. What would I do with that x, right? So what I'm going to do instead is I'm actually going to start by multiplying by square root x over square root x. See what happens here. We end up with just an x on top, and on the bottom, I'm going to go ahead and I'm just going to leave this in its factored form, and I'll show you why in just a moment. I'm going to leave it like that. And now what I'm going to do is I'm actually going to go ahead and I'm going to let u be that square root x. All right? Let's see what happens when I do. Du would be 1/2 x to the negative 1/2 dx, or 2 du would be, and I'm going to write that as 1 over the square root of x, dx. Notice that square root of x in the denominator and that dx can now be replaced with a 2 du. So I'm in pretty good shape there, right? Let's do that. So let's see what I've got here. I have got x on the top. Well, isn't that just u squared? Let's write it that way. Over 16 minus u squared. And then the dx and the square root of x on the bottom, I'm going to make that a 2 du. All right, well, you might argue whether or not I've made that any better, but at least we've gotten rid of all the square roots. That's usually a good thing, right? All right, next step. Degree of my numerator is actually equal to the degree of the denominator, which is the other case where we typically do long division. So I'm using every trick at my disposal in this problem. Let's try it out. I'm going to go ahead and do my long division over here. I'm going to write this as negative u squared plus 16 divided into u squared. U squared divided by negative u squared would be negative 1. When I multiply it, I get u squared minus 16. I'm subtracting those. So my remainder is just positive 16. So I have 2 times everything I'm going to write here. The integral of negative 1, the quotient, du, plus the integral of 16 over, and I'm just going to rewrite this in a more normal, actually not necessarily more normal, in an order that I'm going to recognize. I wrote it this way over here, but I'm going to go back to the 16 minus u squared over there. So what have we got? Integral of negative 1 du would be minus u, plus I could pull that 16 out, and that 1 over 16 minus u squared. Okay, that's another one that I think we might recognize. We worked with it kind of recently, right? Isn't that form just this one right here? I'm going to go with this first one, the inverse hyperbolic tangent. We know it actually depends on where the absolute value of x is, but I'm going to write it as the inverse hyperbolic tangent here. My a would be 4, and instead of x I have a u. I've already pulled the 16 from the top down in front, so I would have 1 over a would be 1/4 times the inverse hyperbolic tangent, and our x is really u over our a, which is 4. Again, I won't worry about the plus c till I put everything back in at the end. Phew, all the integrals are done. Yay! Let's see if we can finish this one up. That would be a negative 2u, but u is actually the square root of x way back up here. Plus, let's see, that would be 4. Distributing the 2 times 4, I get 8. Inverse hyperbolic tangent. Again, u was actually the square root of x over 4. And that's what I have to combine with what I had over here to get my final answer. So I'd have a minus 2 square root x, and then a plus 8 times that inverse hyperbolic tangent. And then I'll finally throw my plus c on there, and we are done. Okay. All right, if you're kind of going, holy cow, that was a lot, and I don't know if I'd have thought of it all. We're going to practice, obviously. We're going to do a lot more integrals. This was just an example of how, in fact, a lot of different techniques can actually end up getting combined in just a single problem that didn't look all that hard to begin with, right? And yet it was a big mess by the time I got done with it. So that's what happens with antiderivatives. All right, our last technique is actually one that we've kind of cheated and used already, the long division. So let's take a quick look at this, but it's probably one that you don't need all that much with since we've already dealt with it. All right, when the integrand is a rational expression and the numerator's degree is larger than the denominator's, rewriting the problem with long division can be useful. And actually, there really is, I've been saying it, and there's a little typo in here. Actually, I should have said with the numerator's degree larger than or equal to the denominator's degree. So here's a couple of examples like this. After the one we just did, these won't be too bad. Let's just go ahead and run through them. Clearly the degree on top is the same as the degree on the bottom, so I'm going to employ that long division technique. 2x divided by x is 2. Multiplying gives me 2x minus 4, and I do have to subtract, so the remainder is 3. So I'll rewrite my integral as the integral of 2, the quotient, dx, plus the integral for the remainder would be 3 over x minus 2 dx. First one's easy, 2x. And the second one really isn't very hard either. What we'd want to do is just let u be the denominator. So du would just be 1 dx. And we'd have the integral of, so I'll pull the 3 out in front, and then I'd have 1 over u. Du is just the same as dx, and that's going to give us our natural log. It would be the natural log of u, or in other words, the natural log of x minus 2. So not too bad. Let's do just one more. Degree of the numerator is definitely bigger than the degree of the denominator. So I'm going to go ahead and divide. I'm going to rewrite this so that the polynomial is in decreasing order. Negative x to the 4th plus 6. There's a lot of missing terms in there, so I'm going to leave myself some space in case I need them. Negative x to the 4th divided by x squared would be minus x squared. We'll multiply to get minus x to the 4th minus 2x squared. And again, I have to subtract, so that makes them both positives. 0 here, and I get 2x squared plus 6. We'll continue to divide. 2x squared divided by x squared would be a positive 2. Multiplying gives me 2x squared plus 4. And once again, I have to subtract. So my remainder is 2. So I'm going to rewrite my integral as the quotient, negative x squared plus 2 dx, and then another integral for the remainder, 2 over x squared plus 2 dx. First one's very straightforward, negative 1/3 x cubed plus 2x. And I don't think the other one's too bad either. We would have a plus, pull that 2 out in front, and then I think this is just one of our standard ones we can look up. Let's see, what have we got here? Looks like this, doesn't it? Where can I put that so we can see it? There we go. Our a here would actually be the square root of 2. So I'd have 1 over the square root of 2, and I'm going to write that as arctangent. x over the square root of 2. And then finally our constant of integration. Okay. Not a whole heck of a lot that I can or need to do here. Let's see. I'm sorry, you guys, I just realized I did not do the problem that was written. I, for some reason, wrote that as x squared plus 2. It's fine. Let's just change the original problem. We're not going to go back and do it now, right? Sorry about that. All right, so again, not a whole lot I can do to simplify. 2 divided by the square root of 2 is the square root of 2, so maybe I'll just simplify that tiny little piece and call it a day. All right. Oops, I said that was the last one. I guess I lied. There's one more. This last technique is completing the square. Just another algebra trick that we can sometimes use. Here I've got an integral. Again, I always start by saying, hey, let's make this as simple as we can. Could we just let u be the denominator? And unfortunately, the derivative would be 2x minus 4. I have the x, but then minus 4 would mess me up. This denominator is non-factorable. That's going to come into play more later on. But when I do have a situation like this with a non-factorable denominator, that's when I'll typically use this technique of completing the square. So let's give it a try. We would go ahead and let's rewrite this. So I have, you know what? I'm going to change this. Let's just put a constant on the top. I think I'm going to make that a 5. This one's going to be a little more than what I wanted to tackle quite yet, if I don't. That'll make it a little better for us, I promise. Denominator right now is x squared minus 4x. I'll leave myself a little space to complete the square, and I'm going to put that plus 8 out here. All right, completing the square, half of 4 is 2. 2 squared is 4. And if I add the 4 inside the parentheses, I'll also subtract the 4 outside the parentheses. Can't really change the value of the expression, right? So now I have 5 over. That'll become x minus 2 squared plus 4. And now I think we're in pretty good shape. We're very, very close to that again, aren't we? The only thing is, I probably want to let u be x minus 2, so I can just get like a u squared plus 4, and then it'll match really, really well. So let's make that little u substitution. I'll let u equal x minus 2. Du will just be 1 dx. And that way my denominator becomes u squared plus 4. Now I'm in pretty good shape. The 5 I'm just going to bring out in front. In fact, if you want to, you can think of bringing it out right here, just making that numerator a 1. It fits perfectly then. What have we got? An a value of 2. So I'll have 1 over 2 times the inverse or arctangent of u over 2 plus my c, or 5/2 arctangent x minus 2 over 2 plus c. All right, let's do one more completing the square. This one was just kind of on its own down there. This one's under a radical. Let's just take a look at how that does or does not change things. It's actually not even the radical that's throwing me off down here. It's the fact that I don't just have a plain 1x squared. I have a negative x squared. I'm going to factor that negative out. If it had been a 7x squared, I would have factored out the 7. I've always got to complete the square when I just have a plain old x squared. Now that negative is going to have to stay under my radical. And that will become x squared plus 8x. And then I'm going to end my parentheses. Then I've got this minus 7. Notice that it is still a minus 7. I didn't factor the negative out of that because it's not inside my parentheses. All right, inside the parentheses, completing the square, half of 8 would be 4, squared would be 16. Now be a little bit careful right here. That 16's in the parentheses, so the minus sign applies to it. So to compensate for a minus 16, I'm going to have to put a plus 16 out here. It should still be under the radical though. I know it kind of looks at first glance like we really added 16 twice, but we didn't, right? This one's a minus 16, this one's a plus 16. All right, so what have I got here? Negative 7 plus 16, that's 9. And then I'll have the minus, and that's x plus 4 squared. All right, kind of like the last time, like here I had to let u be the x minus 2. Let's do the same thing here. Let's u be the x plus 4. So once again, du is just 1 dx. I'm going to write that as 1 over the square root of 9 minus u squared, and that dx, I'm just going to write it as the du over here off to the side. And that, again, looks a little familiar to me. Looks just like this one, right? The a would be 3 here. Since a squared is 9. And our x would actually become u. So I'd have the inverse or arc sign of u over 3. And to finish then, I would have the arc sign of u, which is x plus 4 over 3, plus c, and I'm done. All right, so if you're thinking, holy cow, that was a lot of ideas for one section, it was indeed just the first section here of Chapter 7. But most, if not all of these, are either things that we've seen before or slight variations on things we've seen before. So as you practice, just kind of keep in mind it's also an opportunity to kind of refine some of those substitution skills that we haven't used for a while. And that brings us to the end of 7.1.